like derivative of this and then minus, then I'd have a product rule here. I could do it that way, but I'm just going to do this instead. So product rule right here. What's derivative of the first one? E to the negative x times negative 1, right? So negative e to the negative x, that's the derivative of the first one, times the second one, plus the derivative of the second one, be careful, negative 1, times the first one. I think I'll clean it up. I'm going to distribute here and here. So we'll have negative e to the negative x plus x e to the negative x. That's distribution through here. And then down there I still had a minus e to the negative x, right? Can I do anything with that? This and this are like terms, so I can put those together. That's minus 2 of them, right? So we have x e to the negative x minus 2e to the negative x. There's my second derivative. And if I was so inclined, I could again pull out an e to the negative x. Right? They both have e to the negative x, so I could pull that out, and then I'd have x minus 2 left inside. Any questions? Set that to 0, yes? So setting that thing equal to 0, second derivative to 0 means I set this to 0. What's the only answer? X is 2. How about second derivative not existing? Not going to worry about it, right? I don't have any division by 0. So one number on the number line, right? And it's not 1, it's 2 this time. 2 test points. So 0 and 3. These are going into the second derivative. I was asked by one of your classmates whether or not the third derivative tells you anything about the picture, the shape of the graph, and it really doesn't. The third derivative, I mean, you could probably really try and squeeze something out of it and have it be connected to your picture, but it's, in terms of what we're doing in here, there's no real good physical representation of what the third derivative means. So that's why we stop at the second derivative, all right? Otherwise, we would be doing it. Like the third derivative then shows us that this is doing this. Yes?
I have a question about like what the second derivative looks like.
Mm-hmm.
Because like on the first derivative, like if we're on a parabola, the first derivative is like just a straight line off of the point of the parabola.
The derivative is the slope of that line.
Yeah.
Mm-hmm.
So it's this, right?
Yep.
On that parabola.
Yep.
Then if the second derivative is like the derivative of the derivative,
Mm-hmm.
well, the slope of this line, like, wouldn't it just be the same line?
Well, I think the way you're looking, see, when you're saying that you take a function, right, and you go to this point and you look at its derivative, right, then you're looking at the derivative as being that line. But the derivative is not that line, it's the slope of that line, right, which means that it has some numerical value.
Yeah.
The derivative itself, right, the derivative, if I were to say, hey, look at this parabola, what is the derivative of the parabola? The derivative of the parabola is a line of slope 2x, because this is x squared, right? So if this is x squared, then the derivative of this is actually a new function, 2x, right? And if I go to a certain x value, whatever, let's say 2, plug it in, I get 4, that corresponds to the slope of that line right there would be 4. So trying to visualize the second derivative in terms of this line really doesn't make a lot of sense, because you're looking at, how do I explain this? You're trying to visualize a function But you've already limited yourself to looking at a single point as opposed to like an entire domain, if that makes sense.
Yeah.
What is the derivative of this? What is the derivative of this? 2. So that would be another line, right? That would look like that. So if I graphed all of them together, you would have the function, its derivative, and its second derivative all together, right?
Yeah, I was
Okay,
just trying
yeah.
to think of it like graphically.
Yeah.
And I was like, this doesn't.
The only way you can think about the second derivative when you're looking at a specific point is that if the first derivative is positive, you got increasing, right? And if the second derivative is positive, then the function lies above all of its, it lies above the derivative, so therefore you've got the concave up. That's the only way you can really visualize the second derivative at a point, is by thinking about where the function is relative to that tangent line. It's either above it or below it.
Gotcha.
Okay, so y'all tested these points already for me? What did we get? At 0, we should get negative. So this thing goes down. And at 3, if you plug 3 in, is that our second derivative? Yeah. If we plug 3 in here, we should get positive. So concave up. So we have an inflection point, yes? And it happens at, I'm going to plug it in, 2. I'm going to plug it into the function again. So at 2, what do I get in the original function? 2e to the negative 2, right? Which is the same as 2 over e squared. That's like an x and a y coordinate. It's a point on our graph, isn't it? And the reason I'm doing it and getting the point is because I'm about to plot it in a little while. I'm going to plot this point. So I may as well get the value of it now. All right, I think we are through. We're ready for the Bobby method, right? What goes on our number line? Or sorry, what goes on the table, the number line for the table? 1 and 2? No. Straight up. 3 rows. This is our first derivative, second derivative, and overall look of the function. Okay. F prime. To the left of 1, what was it? What were we doing to the left of 1 from the first derivative?
Increasing.
It was increasing. And then between 1 and 2? Decreasing. And between 2 and on? Decreasing. Okay, second derivative. To the left of 1, we're down, right? Concave down. To the left of 2, we're still concave down. And to the right of 3, we are concave up. How do we go up a frown? Which side of the frown are we on? Left side. How do we go down a frown? Right side? Down a smile? Left side. Is that clear to everyone? That part? Okay, below this. 1, 2. And I'm also going to put 0. Why am I going to put 0? Because that was one of my x-intercepts, wasn't it? Wasn't that an x-intercept? Okay, 0 here. Here's my y-axis. Al, you all right? Question?
I just have a question on the concave, sir. I apologize.
No, don't apologize.
I understand from 0 to 2, it's concave down.
Okay.
Right. But when you go to your chart, this Bobby chart,
Uh-huh.
I'm lost.
This is saying that we're concave down everywhere to the left of 2. Everywhere. This was only a test point, right?
Oh, everywhere.
So this means everywhere to the left of 2. So if we would have picked like negative 100 over here, we would still get a negative number. Yeah. So that 0 really doesn't factor into our picture at all. Is that okay?
Yes.
Okay. So I've got this point. Do I have any other points? Yeah, like what was happening at 1? Didn't we have a local something at 1? A local max. What was its value? E to the negative 1 or 1 over e? So on your calculator, if you do that, that's about what? 0.36 something? And then at 2, it was 2 over e squared, which is going to be like 0.2 something. So here's what I'm going to do. I'm going to make this like 1 right there, okay? This is 1. And that way when I go and I do 1 over e, which you said was 0.36. So this right here, this is about 0.3. Let me say that's 1 over e, about right there. Right, halfway, 0.4, 0.3, close enough. I have a point right there. And then 2 over e squared was like 0.2 something, so 2 over e squared is about this high. We're eyeballing this, okay? And then over here, the important thing is that point is positive. It's above the x-axis and it's below this point, right? Anything else I have? I have a horizontal asymptote out the right side. This thing should flatten out, yes, to the x-axis. And what about the left side? It's supposed to go down, right, forever? I think that's enough. I think we can draw it. So we come down and we look at 1, right? To the left of 1, I'm supposed to look like this. And I have to get from here to here, and I have to continue to go down forever. I think that's pretty clear. It's got to look like concave down. So like that. And then between 1 and 2, I've got to look like this, right? That's going to be a little tough. Let me try. Ah, shit. I'm not real happy with that, but move that point up just a little bit. There we go. I want that to be a local max, okay? So I want it to drop on both sides. But it is part of a frown. And then over here, to the right of 2, I've got to look like that, right? So I'm going to just like this. There we go. That's it. Doesn't have to be perfect, all right? But you should have, all the elements should be there. This was x times e to the negative x. I don't know. Again, I like mine more. I like ours. I'm claiming it as mine. I'm sorry. I'll include you.
Did you call it another name before Bobby?
What's that?
Did you call it anything else?
I didn't have a name before it was called Bobby. No. It's just the way it made sense to me. Okay. Yeah, you satisfied? Is that okay? All right, so maybe we should go after that next one. And this will probably be our last one, right? Time-wise. Or do we want to go after something really bad?
Might as well. It's the last one.
You're at the last one, right? Let's do a trig one. Let's do a trig one. I know we could do that one with the square root, but let's go for a trig one because we haven't done one. F of x equals sine x over 2 plus cosine x. All right. First, domain. All real. Why all real? This right here, we have to worry about division by 0. We do. But the thing is, on the bottom, if we ask ourselves, could the bottom ever be 0? You have to solve that equation, right? And this means cosine of x would have to be -2. but cosine is bounded between -1 and 1. So that's not going to happen. So we should have all real numbers. We should have a picture everywhere. Make sense, everyone? Okay. All right, what about X-intercepts? Set the top to 0. Uh-oh. Set the top to 0. So when is sine 0?
0.
So if we go to our unit circle, right, sine is the y-coordinate. That happens here, and it happens here. But it happens, you can keep going around, right? So this is infinite solutions. X has to be n pi, any multiple of pi, right? 0, pi, 2 pi, 3 pi, 4 pi, or you could go negative pi, negative 2 pi, negative 3 pi, negative 4 pi, right? So all multiples of pi, pre-cal. How about y-intercept, sorry. So 3, your y-intercept, you're going to plug 0 into the function. So you get sine of 0, which is 0, right? Over 2 plus cosine of 0. Cosine of 0 is 1. So you get 0 over 3, right? Which is just 0. We just want to make sure. I mean, we knew we weren't going to get division by 0, but just to be clear, that's what we're getting out. So isn't that the origin again? God, we keep on getting the origin. Obviously, not every function goes through the origin, right? Okay, just every example I've done today has. Fourth step. Oh, no, this was still part of the second step. I apologize. The third step was the symmetry, right? Let's skip it. All right, how about fourth step? Let's go with vertical asymptotes first. Do we have any? No, our denominator is never 0. We already knew that from the domain, didn't we? So none here. But horizontal. Got to look at two limits. Limit x goes to infinity of sine x over 2 plus cosine x. This one's a little bit tricky. If you let x go to infinity, where does your numerator go? It's just doing that, right? And so is the denominator. It's 2 plus this, but that's doing this, right? So this limit actually does not exist because you're not headed to anywhere, right? They're just oscillating, but it's not headed to one value. So I think this is the first time we've ever had this, right? Limit doesn't exist. And because that limit doesn't exist, we don't have a horizontal asymptote. And if we go to negative infinity, we're going to get the same thing. Because we, think about the sine function as we go to the left this time, it's going to oscillate the same way. So I'm just going to change this to plus or minus infinity. We're getting the same result, both directions, that the limit doesn't exist. Now, let me just ask you, what if the denominator was not 2 plus cosine x? What if it was like x squared? Then what? You'd have bounded over infinity, and that goes to 0. All right, so just keep in mind there's different things that could happen. But in this case, the fact that the limit doesn't exist on the top and it doesn't exist on the bottom leads us to not existing overall. All right? All right, derivative time. A little quotient rule here, right? A little quotient rule. We're not afraid of quotient rule anymore. We're pros. Pros. All right, derivative of the top is cosine x times the bottom. Looks like we're going to be solving a trig equation. Minus the derivative of the bottom. What's the derivative of the bottom? Just negative sine x. And then times the top. Sine x again. All over. Bottom squared. Let's go ahead and clean up that numerator. Distribute. So we should get 2 cosines of x plus cosine squared x plus sine squared x all over 2 plus cosine x quantity squared. Really? Okay. All right. So do y'all see it?
And then just 2 cosine x plus 1?
Yep. This is our Pythagorean identity, right? That's 1 all the time. 2 cosine x plus 1 over 2 plus cosine x squared. Okay, I think that's about as good as we're going to get it right there. Right, we can't cancel anything here? Like nothing, please don't do that. Okay, now what? Yeah, we got to figure out when it's 0 first, so we're going to set the top to 0. When's that derivative 0? Well, we just set the top to 0, and guess what we have again? Another trig equation, right? And it's going to have an infinite number of solutions. We want to know when cosine of some angle is -1/2. And so I go to my little unit circle. Cosine is the x value. And where is it -1/2? Here and here. And unfortunately, these are not directly across from one another. So we have to look at the general solutions separately. So this general solution will be x is equal to, well, what is that angle? We're going to do it in radians. This one should be 2 pi over 3. 2 pi over 3. How do we get back to it? We have to be able to get back to it. Plus 2 pi n or n pi, 2 or n times 2 pi. You can put the n in front or the back. Doesn't matter where it is. And then we have to get this solution. So, or x equals, what's that, 4 pi over 3 plus 2 pi n. So if you're like sitting here like freaking out about these trig equations, I would just put a star next to it and go get some tutoring or come by my office, because that's all pre-cal stuff. And I'm happy to go over it, just I'm not going to go into more detail than I've done here. All right? So if you go to tutoring and say, I need help finding the general solutions of trig equations. Okay? All right, that's it, right? Done with that? Oh, where's the derivative undefined? So where's the derivative not exist, or where's it undefined? Well, that means where's the bottom here 0, right? Which can't happen again. We've already kind of looked at 2 plus cosine x, so we don't have any issues. So now what? Number line. Uh-oh. How many numbers do we have to put on the number line? Oh, just infinitely many. Okay. All right. Okay, well, we're just going to put enough to get a feel, all right? So here's our number line. Let's see, we had 2 pi over 3, didn't we? Another one we have is 4 pi over 3. What would another one be?
5 pi.
5.
8.
So here's a way you can do this that I think, at least for me, there's kind of 2 ways that I'd approach this if I needed to figure out more of these. One approach would be take the formula you have, right? This was it. And just start plugging in different values for n. So if n is 0, you get 2 pi over 3. If n is 1, you get a different answer, right? But before you start plugging in values, what you do is you get a common denominator first. Right? So get a common denominator, and then put them together. So you have 2 pi plus 6 pi n over 3. And remember, you cannot combine these together because this one has an n and this one doesn't. So now if n is 0, you get 2 pi over 3. If n is 1, you get 8 pi over 3. If n is 2, you get 14 pi over 3. And you can start cranking them out pretty fast that way. That's one way to do it. Another way to do it is go back and look at your solutions here, or your 2 points. Okay, and hold on. Okay, so if you look at it this way, Sorry, these are the answers, right? These are not answers. Okay, so this is pi over 3, right? 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, 6 pi over 3, right? 7 pi over 3, 8 pi over 3. Nine pi over 3, 10 pi over 3, right? Eleven pi over 3, 12 pi over 3. Where am I? 13? 13 pi over 14 pi over 3, which is, we got that 14 pi over 3, right? So that you just kind of count your way around. Let's just go with that, okay? Those 4 points for now. Just realizing we have an infinite number of these, right? So now we break this up, and we get to pick test points. Crap. Okay, so this again, this will help if you understand this. What is a test point between here and here? So between here and here, right? Between these two. How about pi? What is a test point between, 4 pi over 3, which is here, all the way back to 8 pi? Anywhere between here and here. You can't say 0 because we've gone past 0, right? This is 0, 2 pi over 3, 4 pi over 3. We'd be back here at 2 pi. That's 2 pi, right? So 2 pi is between these two. Right? Now we're looking for another value between here and here, because this is now 8 pi over 3 and this is 10 pi over 3. 3 pi would be there. Let's get one more over here. How about this? What would that be? We could do 4 pi. And how about back here? Let's do one more over here. Something between, right? How about 0, right? 0 would work. All those test points get plugged into what? The first derivative, which is this. Okay, so let's see if we can do this. Let's plug in 0 first. What's the first derivative at 0? All right, so 2 times cosine 0. What's cosine 0? 1, right? So we're going to get 2 plus 1. That's 3 on top. And on the bottom, well, the bottom's always squared, isn't it? So the bottom's positive no matter what. So this is going to be, our original function here is increasing. Now plug in pi. What's cosine of pi? -1 times 2, -2 plus 1, -1. So top's negative, bottom's squared, always positive, right? So now we get negative. Decreasing. Okay, what about at 2 pi? 2 pi is basically the same angle as 0, so you're going to get the same answer that you got here. So this is going to be increasing. And then 3 pi is basically the same as pi, so you're going to get decreasing. And it's just going to keep switching. Increase, decrease, increase, decrease. Second, oh, do we have local maxes? Oh, do we? Yes, we do. We have local maxes. We have local maxes at 2 pi over 3, at 8 pi over 3, right? An infinite number of them. And we have local minimums. Local minimums at 4 pi over 3, and 10 pi over 3, right? So at every one of these, right? At every one of these, we have a local max, and every one of these, we have a local min. Let's keep that in mind. Second derivative. Running out of time. Second derivative. Quotient again, right? Quotient again. So what's the derivative of the top here? -2 sine x. Okay, times the bottom. Minus, chain rule, right? Chain rule on that bottom. Derivative on the bottom. 2 times 2 plus cosine x times negative sine x, that's your chain rule, times, in parentheses, 2 cosine x plus 1. Remember, I'm the messenger? I'm the messenger. I like just typing it into Desmos and having it graph, don't you? Any questions on that derivative? Yeah, that should be to the 4th power. Thank you. What in the world are we going to do with that? Yeah, they've got common factors again. So let's start looking at numbers. Let's see. We can pull a -2 out of this and that, right? We can also pull a sine x, right? I could pull a negative sine. Let's just pull sine x out. Sine x came out. Any other factors? 2 plus cosine x can come out of both. And anything else? I think that's it. Okay, so now what was left here when we pulled all this crap out from here? Just one of those, right? Just this? Just one of these. Because we pulled that out, and we pulled one of those out. So we should just be left with 2 plus cosine x. This one I won't leave in parentheses. I'm just going to put it here. And then what's next? Do I have plus or minus? Minus, right? Because even though I pulled this negative out, I still had a negative on the sign. Right? So I still have a minus there. I pulled the 2. The -2 is gone. I pulled this out, didn't I? And then I pull that sign out. So I still have that, right? That's the only piece I have left. So I should put that in parentheses. All over denominator to the 4th. God, we still have to make a table. All right. I'm sorry? Go ahead. What? Like one of those again? Like, is that what you're saying? Like this and that?
Well, that in.
Oh yeah, I'm going to clean this up. Yep. So one of those is going to go away. We get 3rd here. And when we clean that up, I'll go ahead and just write it nice and condensed here. -2 sine x. When I do that, I get 1 minus cosine x. Somebody agree, please? Yes, okay, and then on the bottom, 2 plus cosine x cubed. So all we did here is just distributed the negative through and then combined like terms together to get that right there. All right, got to set that to 0. Got to figure out where it's undefined. I'm going to leave this up, okay? I'm going to leave that up. So if I set that to 0, let me do that right here. If I set that to 0, I only have to set the numerator to 0, right? And the numerator is -2 sine x times this. So really, I just have to set sine x to 0 and that to 0. -2 I can ignore, because -2 can never be 0. So I just need to know when sine of x is 0, and what else? When 1 plus cosine x is 0, right? Which is same as saying when cosine of x is 1, right? So when is sine 0? Those 2 points, pi n or n pi. And when is cosine of x 1? Only at that point, right? Only there. So 2 pi n. But doesn't this cover it? This covers those answers, right? So if I just say that, it's going to include all of those answers too. So this would be sufficient for us to just look at that. Is there anywhere where this thing is undefined? No. No. Okay, so now number line. Shoot. This is the drawback to working on a board that's only, about 8 feet by 4 feet, 5 feet tall. Yeah. Okay, so number line. And I'm basically putting on this all multiples of pi. 0, pi, 2 pi, 3 pi, right? I could go in both directions. Test points, right? So pi over 2. What's something there? 3 pi over 2. How about here? 5 pi over 2. Next one would be 7 pi over 2. Right? So basically on the circle, what I'm doing is we've got to get between these, right? So we pick a test point here at pi over 2, then at 3 pi over 2, then at 5 pi over 2. So something in between those two. And those get plugged into the derivative, second derivative, which I erased, but believe I remember. Was that it? Okay. So that's our second derivative. All right, let's do pi over 2. What's sine of pi over 2? 1. So we get negative 2. What's cosine of pi over 2? 0. So this is going to be 1. So we get negative 2 times 1. So we get negative 2 on top. On the bottom, look, no matter what this is, plus 2 is positive. Because the worst this could be is negative 1. So if I add 2, it's going to be positive. So the bottom's always positive.
And all of our points, cosines.
Pardon?
All of our test points, cosines always zeros.
Yeah, and then all these, this is always going to be 0, so that's always going to be 1. So really it just comes down to this, doesn't it? Just comes down to this. So here we were at negative 2 times 1, which is negative 2, so we're going to be concave down here. And then at 3 pi over 2, sine of 3 pi over 2 is negative 1, but then we hit it with negative 2. So now it becomes positive, and these are both positive. So positive, concave up, concave down, concave up, concave down, concave up, concave down. So where do we have inflection points? Every multiple of pi, we have an inflection point. All right, let's try and draw this because I am really getting close to out of time. Y'all ready for the picture? Let's get the picture. Let's try and do it, all right? Original function. I'm going to put it on the side here. I've forgotten what it is, but I think it's sine x over 2 plus cosine x. That's the original function. All right, here we go. I'm really going to need your help here. Here comes my table. I've got to put all the points that were kind of important to us. So 0 was on there, right? So was pi. So was 2 pi. So was 3 pi. And we get to kind of decide how far we want to go with this. I'm going to go out to 4 pi right now. I don't know if I'm going to draw it that much of it, but all right. Those were from our second derivative, weren't they? Okay, now from our first derivative, we have these, right? We have these guys right here. So where is 2 pi over 3? Isn't that like over here somewhere to the left of this? This 2 pi over 3. Where is 4 pi over 3? A little bit to the right of this. Yeah? Where is 8 pi over 3? Past 2, before 3, right? So somewhere like here. And then the next one after that, 10 pi over 3. I'll stop there. Straight up, 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 over. We see how fun these can get? Okay, F prime, F double prime, F. Let's talk first derivative. And I've got it on the board there, so this is wonderful. To the left of 2 pi over 3, we're up. And then I'm going to go down until I get to where? 4 pi over 3. So that's down, down, right? 2 little places there with downs. And then from 4 pi over 3 all the way to 8 pi over 3, I'm what? Up. So I got 2 little up regions here. Up, up. And then 8 pi over 3 to 10 pi over 3, I'm down, down, down. And then from 10 pi over 3 on, I should be up. So I'm just going to go like that. Okay? Does everyone understand why we have multiple arrows going down? It's because our region's been broken up by the second derivative. Okay. Now, for the second derivative, I've erased this, but I think it was down. It was down all the way from 0 to pi. From pi to 2 pi, it was up, concave up, and then concave down, then concave up, and then it'll go concave down again. And so now it's all about left side, right side. Left side frown, right side frown. Left side smile, right side smile. Left side smile, frown, sorry. Right side frown. Left side smile, right side smile. So it's behaving a lot like we think it would behave because it's trig, right? It's a bunch of up and down stuff. Oh man, this part's going to really be bad. Were there any points that we knew about that existed on this graph? 0, 0, yay, yay for us. Okay, here we go. We got 0, 0, yay, that belongs to the graph. Okay, other than that, we need to figure out all of these points, what's happening at every single one of these. So I need some more points, right? To get a good graph, I got to get some points on my graph. I know what the shapes look like between them. I just need to plug these values into the original function. Now, do you all agree? No, that's not worth saying. Never mind. All right, let's try plugging in 2 pi over 3. So what is sine of 2 pi over 3 over cosine? Oh, sorry, it's 2 plus cosine. 2 plus cosine of 2 pi over 3. So what was sine of 2 pi over 3? Root 3 over 2. So we're going to our unit circle, going to 2 pi over 3, which is here. That has the order pair -1/2, root 3 over 2. So sine of that should be root 3 over 2 over 2 plus, what's cosine there? -1/2. So we get root 3 over 2 over, oh wait, we're out of time? Over 3/2. And so that becomes root 3 over 3. Okay, so imagine going through and plotting all these points now, okay? I'm not going to have time to do that. So here is what it looks like. Sine x over 2 plus cosine x. There it is. See, it fits perfect right on mine. Right, so there was a lot there to, but you can see in the picture, you can see that we've got these inflection points, right? We've got local max, inflection, local min, inflection, local max, inflection, local min, inflection, local max, and it just keeps on doing that. So it is what it is. Okay, so test is on Thursday, right? I sent out the thing to look over. Yeah, see you Thursday. Have a good, I'll be in my office on Thursday before class. If you want to come by, 9 o'clock to 1 o'clock.